Hello, hello. Oops. It's a bit. Sorry, it's just wobbly. Thank you for having me. My name is Zoltan. I'm a senior software engineer at IBM Research in Switzerland, working in IBM Research Europe. And I've been focusing on Velox and for like 2 years, and specifically for GPU accelerated data processing over a year now. And I would like to give an update to this journey, right? Yeah, so this is a joint effort. So this is really a joint effort with NVIDIA, where a lot of folks are from NVIDIA and they're growing the team, and also from IBM, where we focus on how we can do this together with a split focus, because the goal of NVIDIA is to make QDF, which is their data processing library, faster and integrate to Velox, while our goal is to make the whole system faster with multi-GPUs, right? And to talk about how it works, is what we do is when Velox comes up with a plan comes up with a physical plan through the local planner, then we replace the operators to GPU native operators, right? So whatever NVIDIA's QDF library ships, we support, right? So for example, for aggregation, if the QDF library has aggregation, then we just replace that operator in the pipeline once it's planned, right? And I realized, we just dived right into the nitty-gritty of how it works, right? I just assume that most people, know that GPUs are ubiquitously there because of our AI and ML progress in the last couple of years. And they just, AI researchers, they just always want the latest. So the old GPUs, they are already available, right? And lots of companies are looking to move from the old generation of GPUs to newer generation of GPUs, because for AI and ML training, the ROI is on the new hardware, right? But the question is, for data processing, can we use this old hardware? Or is it junk, right? Is data processing always better, same as ML workloads on the latest hardware, right? And to answer that, we needed to integrate it and then benchmark it, right? And then we finally got to the, by October, we finally got to the stage where we can actually have numbers and we could actually run real queries on the system. And to give you some first numbers, basically what you see is the blue bar compares a workstation class AMD CPU, and then we compare it with two different systems. In the middle, you have the Pro 6000 Blackwell GPU, which is something that I realize in China the GPU question is difficult, but generally speaking, you could buy that as a workstation GPU. And then we compared that to a complete system, the Grace Hopper system, which is a complete 1U platform integrated, right? And we were curious how much faster can we run this if the data is not on the GPU memory, right? So the data gets loaded. Same for the CPU, the data gets loaded. Actually, for the CPU, there's an advantage because the data is already in CPU memory. And for the GPU, we need to transfer that to GPU memory, at least on the Blackwell system, right? And you can see that roughly, I'd say we're around 9x faster on TPCH. Now, this can be improved, right? So when looking at profiling on how much do we actually use the system, I would say around 10%. So I think with clever engineering tricks over the next year or so, we could double, triple, or 5x this, right? So this is just the beginning of this. And you can see that on some systems, we can't run all queries, so that's why it's only 21 queries, because one of the TPCH queries runs out of memory on these GPUs. And if you want to use that, you need some tricks, right? Because currently, for normal CPU workloads, we can easily move data in and out. For GPUs, this is a bit more costly. Moving data is costly. So you want to avoid moving data, and you're limited on the GPU memory size, right? Much more limited than on CPU size. This is changing, right? So as you see the new releases of GPUs, the GPU memory size started growing as well, significantly growing, right? We went from 80 gigabyte in 2000, we went to half a terabyte basically this year, right? And I think in the next 2 years, this is going to double. So we're going to get significantly more GPU memory, right? And then, of course, what happens when you run something like a join, right? You can see that if I want to run a join, I need to build my hash table, which is usually random access memory intensive. And thanks to the HBM memory on the GPU, this is much faster, right? So the 5-year-old Ampere can do that, the hashing build at around 90 to 160 gigabytes a second, right? And then you want to do a shuffle, and then you can do the actual probing. Another thing to realize about GPUs is that if you want to take advantage of this, if you want to make the shuffle, we know that the hashing is fast and we know the probing is fast, so we need to make the shuffle fast. And the question is, how do we make it fast, and why can we make it faster, right? Now, on a normal GPU system, this is a 5-year-old GPU system, what you see is that you kind of have these 4 PCI switches, and south of them you have the GPUs. But you also see that the GPUs at the bottom are connected with their own high-speed interconnect. So if Velox could take advantage, the Velox workers, if you imagine this to be 8 workers, if the Velox workers could actually take advantage of the bottom bandwidth instead of going through the CPUs to do the shuffle, then you could be much faster, right? That much faster. So by moving the data from the normal Presto exchange to a exchange that actually can use any transport, so not just NVLink, it can use TCP. If you have InfiniBand or you have Rocky, then it can use those networks, right? Then you get around roughly a 6x performance. This depends on if your query does a lot of joins, you get better speedups. If your query doesn't do a lot of joins, then the speedup is negligible, right? If you just run aggregations everywhere and then a final aggregation, then it doesn't matter, right? But the aggregation is still going to be faster, right? And then this exchange, which we call QDF exchange, it's built on UCX, which is an open source project on GitHub by NVIDIA, by AMD, by Intel. So it really supports all the transports out there. It's not tied to NVIDIA hardware. We just built it on this because we had the hardware, right? Now, let's see why can't we go faster, right? If you look at the breakdown of TPCH, you'll see that we spend around 61% of our time just on parsing Parquet, right? And if for CPU, the number is not so drastic, but even for CPUs, you're spending, depending on your query, you're spending 30 to 50% on parsing Parquet, right? It's horrible, right? Especially for GPUs, this is horrible. So we thought, what could we do about throwing Parquet out and replace it with something that's much better for us, right? So as an experiment, what we basically did, we took the Parquet files and we converted them. I'm not sure that's readable from the far, but basically we have the shared file system, and we converted the data to use the file system as metadata. So the file name actually encodes the type, encodes the table name, encodes the column name. And then, since it's a shared file system, we wanted to use one more trick to speed up reading data, which is called GPU Direct Storage, or GDS, in which you can basically, when you read data from the storage, it ends up on GPU memory right away. So you skip CPU memory altogether, right? And if you think back to this picture, every GPU has a network card next to it, right? And I have 8 network cards, 8 GPUs. So if I don't need to go through these switches and I don't need to go through the CPUs, then in theory you could use all the bandwidth from those 8 NICs to drive your 8 GPUs, right? And this is exactly what happens. So in this system, you can read data at 200 gigabytes a second. And then the question becomes, if I can read data at 200 gigabytes a second, is that slower or better than if I need to read compressed Parquet and then decode it, right? The answer is better. This is around 3x faster than decoding Parquet. So with this was just an experimental approach, right? But what the system collectively, you gain from CPUs to this path, you gain roughly 16x performance when you factor in this custom file format, right? Which we understand that, it's just an experiment. This is not meant for anybody to use, right? We just wanted to see the effect of what happens when you can skip Parquet, right? And it works very well, right? So the problem with that approach is that if you move to any cloud provider, and on this picture I have AWS because a lot of our customers are on AWS. On AWS, you would not have GPU direct storage. So you have a lot of GPUs, but how do you feed them, right? You can't put data on the GPU fast enough. And you can see the difference basically between on-prem and AWS cloud. This is on Parquet. So this measurement here does not have the previous optimization. Because our customers, we don't expect anybody to convert their data from Parquet or Orc or whatever they have. We don't want them to convert their data, right? So the question is, if you have a GPU cluster, you have some fast networking to where your data is, how can you marry this? And how can we marry this on cloud providers, right? And actually, at previous VeloxCon in April, Masha and the Meta team generally talked about how they feed their GPUs for pre-training data, right? So we adopted that idea and we implemented it from scratch. So we came up with this idea that we're using Velox, very small nodes, but a lot of them, to grab the data from S3 on AWS or from any object storage, and do the action on the CPU with Velox, do the format decoding, and put it into a format that our GPUs can now process fast, right? So in this scenario, you could imagine that the cache layer there has 1,000 VMs, but they only live very short. If you just want to grab the data, you could scale it out to 1,000 VMs, grab the data, feed the GPUs, and just delete those 1,000 VMs. And this you can do under 1 minute, right? And then those GPUs, what I showed you in the picture, each had 200 gigabit, but that was 5 years ago, right? Today you can get GPUs where each GPU has 800 gigabit. You can feed each GPU from the network at 100 gigabytes a second, which means if you have 8 GPUs in a box, you can feed that at 800 gigabytes a second, right? Almost a terabyte a second of raw data coming in. What this architecture gives us, you can do filter push down, you can do all the transformation of your data with normal Velox plans and Velox pipelines on your CPU nodes. And because we already built the interconnect, we've already built the exchange to take advantage of your interconnect that's available, you can just reuse that code, right? So building on top of that, we can build this cache. And we validated that this idea works, that you can, on AWS or even on-prem where you have separate CPU layers to GPU layers that you can scale independently, and you have some object storage, you can feed the GPUs through this path, right? It's a bit clunky, right? So from a developer perspective, it's clunky today. We hope to clean this up and then contribute it back upstream, right? Velox currently does not ship today an exchange out of the box. Presto ships with its own exchange built in Prestissimo, right? I would very much like to ship this in Velox, right? So looking at the state, and this is through a Presto lens because we're mostly driving our Velox setup through Presto, right? What we have today, the hardware access exchange that I talked to you about, it's in a draft PR upstream, albeit a bit older code, but most of the code is there. We have native integration in Presto for running Velox with QDF on GPUs. So you can today, if you grab Presto today, you build it with GPU enabled, you can run it on your GPU. And then what we're going to add here, to do this high-speed transfer from CPU to GPU, that's not upstream. That code is not upstream today. We need to write that nicer. And then And then you can do elastic caching, and you basically get the speed what you would get from a local storage on cloud, right? Now, one last thing that we've been looking into is we can't really make good decisions at the local level, right? Since currently we're adapting the pipeline to run on GPUs at the local level. This is inefficient because you could take advantage of optimizations that are only available at a global level, right? So we've been experimenting on how to actually change the Presto plan to a GPU native plan, but you don't know at the coordinator level, it doesn't have any idea that it's going to run on GPUs. So we've been looking into enhancing Presto to add capabilities to do a global topology-aware scheduler, right? Which would mean that if you need to do part of a hash join and you want to distribute the hash join, then you try to keep it within your high-speed boundary. Keep it within the box where you have the GPUs, so you don't need to cross a slow link, right? Because if I need to go from a GPU to a remote GPU, not over NVLink, that's much slower, right? And then especially if I need to come back, then you just lose the speed, right? Yeah. And that's all I had, and I'm happy to take questions if any of you has on this topic.